Now we see one other example of a group that, so okay, just to complete this part, we can see very common example of cyclic groups. Pth group of unity, the pth root of unity, the root of unity. So you say x to the power p. The p solutions in the complex plane which are called roots of unity. These p solutions form a cyclic group. So we can draw a little picture here. So draw the complex plane, real and imaginary axes, and let's say sixth order. So hexagon is easy to draw, right? So I find the solutions of the equation x to the 6 equal to 1. They are these 6 points. You know what they are, e to the 2 pi by. So the group is e to the 2 pi I by 6. This list of elements constitutes this group, and clearly this is a cyclic group, 2 pi I r, with r equal to 1 to 6. So this set, this list of elements is a group. It is cyclic group of order 6. Order 6 generated by e to the I pi by 3. Clearly you can have any number of for any p, for any integer p, any natural number p, you have a corresponding cyclic group. Such groups are always commutative. Because they are all made up of powers of only one element, commutative. Okay, because any element, any two elements are a to the power r1 and a to the power r2, right? You can always write them like this. So clearly it's a commutative group. There is another interesting fact, which is that if you have so we'll come to it later. So you can, when p is a prime number, you get some other interesting facts. There are no subcycles and so on. Okay, so I think this is good for the time being. We are building up the group concepts by example. The next group we want to look at is called the 4 group. by 3 is a group of order 3. Yeah, and this is the only group of order 3. Okay, there is no other group, and it's abelian. So, what we are claiming is that this is the only group of order 3 and it is also commutative. So, why are we saying this is the only group of order 3? Well, let us try to write a multiplication table of, E, A and B. Okay, I have 3 elements E, A and B. So, what can I do with them? Well, this first row and first column are fixed already. The only thing I can do with A and A is to make it into a B, right? If I did A and A also into E, I will be forced to do B and B also into E, and I will not be able to say A into B equal to B. So, the uniqueness of multiplication forces that the table is precisely of this form. So, I can only have this particular configuration that I am writing. So, B A will be E and B squared is equal to E, B squared is equal to A. The general point to note is that uniqueness of multiplication. So, AB is mapped into another group element, but this group element has to be unique. That ensures that in a horizontal row, no element of the group can be repeated. It can occur only once. You can't have A times B giving C and A times F also giving C, because then the inverse will not be unique. So, the row can contain an element only once. Similarly, the column can also contain an element only once, because a column is nothing but the reverse, I mean you can think is also a multiplication. So, these two facts, or this fact that the multiplication gives unique elements and the inverse has to exist, that puts a strong restriction on the table you can write, combined with associativity, which is additional, but for a small order group associativity does not enter. This itself has fixed the group table completely, okay, because you can think about it. So, if you try to do A times A also equal to E, so suppose I say A times A squared is equal to E, then I have filled in A and I have filled in E. I am forced to fill up B over here, okay, but that means that A times B is B, but that would mean that A is identity, but identity is unique. So, you can't have two identities. So, the uniqueness of multiplication and uniqueness of identity forces that this is the only, would mean so thus uniqueness of, thus let me just say group properties, all the 4 properties enter: closure, a multiplication, existence of identity which is unique, and existence of the inverse which is unique. Those things force the table to be quite uniquely fixed. and I have left this space to write in each row and column an element of the group can occur only once. In each row and column every element can occur only once. This is one of the utilities of the table. You can use the multiplication table to decide what kind of group you can possibly have to that order. And it turns out that to any finite order you will have only finite possibilities that you can have. Okay, so the next thing I wanted to do was one more example of a group which is called the 4 group. So at order 4 we do have 2 possibilities and we do get a non-abelian group. Sorry, I think this group is also abelian. So at order 4 there is one more group called the 4 group. Called that because some great man called it once, not some great man, Felix Klein. So this is in the early days of group theory, and so let us bring up that table for order 4. So we already drew this table as a possible multiplication table. Let us see if there is any other way of drawing multiplication, EABC this cannot be changed. Oh God, what have I written? EABC. So if we compare with this group, then here we put A times A equal to B. Suppose we try to put A times A equal to C, okay, that is another possibility. But if we try to do this, what will eventually happen is that we will basically trade B and C. All that we will do is end up getting another table where we have traded B and C. The other possibility therefore is that we put E over here. A squared also equal to E. Then that fixes rest of the multiplication table, because A times B now must be equal to C. It cannot be anything else, and then this has to become B. Okay. So this table is filled out by making all the elements squared equal to E, and then the rest is filled automatically, because B times A has to be different from B, from A and from E, so it can only be C, and B times C cannot be B, cannot be C, cannot be E, so it can only be A, and we see that each element occurs once in each row. So similarly here all I can have is CA, that has to be B, and then CB has to be equal to A. So we get a group like this, and we can check that these are all the possibilities we have at order 4. There is nothing else. So you can of course rename B equal to C, B and C, but it will not change the multiplication table. So this by Felix Klein was called the 4 group. I guess in the old days it was a interesting discovery. This group is also commutative, as can be seen from the table. You can see, right, if you look at that multiplication table, if it is symmetric along the diagonal, then it is clearly a commutative group. So this is symmetric along the main diagonal, across the main diagonal, flipped across the main diagonal. This group that we are now drawn up, we can now take a look at it, and we see that yes, it is also symmetric about the diagonal. So it is also commutative. This is the only other possibility. And is also commutative. Now we manufactured an abstract group by hand, just by writing up a table, forced by the group properties and trying to be different from this other group, the cyclic group C4. But now we may ask the reverse question, where can we realize such a group? What is a physical or geometric setting where it is realized? And it turns out that it corresponds to flips of a rectangular figure. The hint is the fact that square of every element has to be identity. So if I take a rectangle, not a square, and then allow for flips about these two axes. So if I flip say 180-degree rotation, then I get back the same rectangle. If I do it twice, I get back to identity. So this flip squared is identity, like we see. So we can call this A, and we can call this B, or call this whatever, and the other one we can call B. If I flip once, I get I should get well, anyway, the flip squared is identity. That is what characterizes the diagonal elements here. If I flip both A and B, then also if I do it twice, I get identity. If I do it twice, I get identity. So the element C is basically a combination of A and B. Okay. So this basically is one realization of the Klein 4 group. So that more or less completes our examples of the lowest order, and we see that the lowest order examples are all commutative. Up to order 4, all groups are commutative. So what we will next do is start with what are called permutation groups. So there are two settings in which the finite groups arise. One are all geometric. You can have a rhombus, you can have various you can have lattices in condensed matter physics, or you can have molecules. So there are geometric shapes and they have their symmetries. The other possibility is more abstract, which is just permutations. You permute objects among themselves and the permutations form a group. So we will take that up next, and we will see why it is actually fruitful to study permutation groups. We will next do permutation groups. Sometimes these are also called symmetric groups. We call it Sn. So, a symmetric group, the group of permutations of n objects is called Sn and will have order n factorial. The group of permutations of n objects is denoted Sn, symmetric group Sn, but this is only a notation because the number of elements in it is n factorial. So, the notation we have, instead of A, B, C, we will just write 1, 2, 3, 4, that is the difference. And I will tell you the reason, because I want to reserve the small letters A, B, C for group elements. So, we say, we write something like 1, 2, 3, 4, and we have not gone to 5 so far, and then some configuration that it goes into. So, this permutation, this is what this represents, is that my original order after the permutation goes to this. Of the objects. Okay. So, this is the notation we will use. As a result, so one thing to keep in mind is that there is nothing very sacrosanct about the top row being 1, 2, 3, 4, 5. I can now actually exchange the columns. I can also write it as we can just permute the columns. I am sorry to use the word permutation too much, but for example, we could do this. It means the same thing. It says object number 3 went to place 1, object number 4 went to the place of object number 5, and so on. Okay. This we may have to do occasionally. We will not in general do it. It gets confusing. We will start with this and say what it went to. But these two are equivalent. The advantage of that is that you can actually make a multiplication rule. If I am given some particular thing 1, 2, 3, 4, 5 goes to whatever that was 3, 4, 1, 5, 2, I can write another element, and just to keep things simple, let me say I wrote this. Now, according to the comment we made here, because that this, so long as it gives correctly 3 goes to 1, 3 goes to 1, then it does not matter in which order I specify the permutation indication, then this is clearly also a particular permutation of 5 objects, right? It just says 3 goes to 1, 4 goes to 2, etc. But now I can use this as a way to multiply, in which I simply cancel this and this. Okay. So if this row is the lower row of this element is same as the top row of this element, I can cancel the two. And get equal to what identity. Then I just compactify and write this down. So to multiply two elements, what you do is, and you know the order in which to do it. So I have an element A and I have any other. So in general, if we want A times B, then arrange top row of A in the same order as bottom row of B. And here the order is important. B is what is happening first. We will, because multiplication is not commutative, we have to remember that writing A O B means that B will act first on whatever it acts on. It's an operation. So B will act first and A will act later. That is the meaning of this multiplication. And so we bring the top row of A in the same format as the bottom row of B, and let the bottom row of A follow whatever fate it has, because you have to move them as blocks, vertical blocks. Then you can cancel off this row and this top and this bottom rows and compactify, and whatever you get is the answer. Okay. So we can do another example. So let us see. So to do that, we have to check the thing. Let us do it in a bit of a detail. So suppose I say that I will take that already as it is. 1, 2, 3, 4, 5 goes to, let us say, 3, 4, 1, 5, 2. Now suppose somebody gave me another operation where 1, 2, 3, 4, 5 went into, let us say, 5, 3, I am just thinking something randomly, 4 remains where it is and 1 goes to, let us say, 5. Suppose I want to do this. Then what I will do is first bring this top row in the same format as this. So we write this as equal to, leave this as it is. Now I make this also 3, 4, 1, 5, 2, and then carefully look here. Where there is 3, there has to be 2 below. Where there is 4, there is 4. Where there is 1, I have to have 5. Where there is 5, I have to have 1. And where I have 2, I have to have 3. Now that I did this, I am free to cancel this and this and write it as equal to 1, 2, 3, 4, 5 and this bottom line here 2, 4, 5, 1, 3. Now how do we verify that this is correct? So one way to think is that you could have drawn it in, drawn it like this. Instead of committing yourself to any notation, just go back to basic enumeration or representation. So all I do is write 1, 2, 3, 4, 5, and then I look at what my element A was. Well, it sent 1 to 3, so that I will write as it is 3, 4, 1, 5, 2. So this operation is my entry B. Now if I want to do A, well, let us look at what is A. I bring back here what is A. A says that 1 goes to 5. That means that I have to replace this by 5. 2 goes to 3. So this is 3. Is this visible? Yeah. So 3 goes to 2. So this becomes 2. And 4 remains 4. And 5 goes to 1. So I have done operation B, and then on the result I have applied A. So what did I get? I got, let us check if it gave, so it is equivalent to doing, it is equivalent to deleting the middle row now, because that was intermediate step, and I have to write, if we want to return to writing in our notation, then the notation says that I write original configuration first, 1, 2, 3, 4, 5, and the resulting configuration, which is the bottom row. Okay. And then we compare with what we got. I mean, it's not a major magic trick, but I'm just saying that what you, if you would do, so these two tally. Okay. That is why this method, which is rather simple, but all you have to do is enumerate carefully. When you are reordering the columns, remember to keep each block together. Each vertical block has to be kept together. So we can say something like this, 3, 2, sorry. So from here to here, going from here to here, the 3, 2 went into 3, 2. Okay. So you have to move blockwise, each column blockwise. Then you will be doing what you would have done logically by writing out everything in detail. So you will reproduce that answer. Okay, so I think we will stop here. We have just introduced permutation groups, and we will continue with that next time.